This lecture is going to cover sections 26.4 through 26.6. We're going to be looking at diffraction, and it's going to be through single and multiple slits. So diffraction occurs when light passes through an aperture or around an edge. For a single narrow slit of width A, the condition for destructive interference or dark fringe at point P at an angle theta from the direction of the incident light is going to be governed by this formula. A diffraction grating consists of a large number of thin parallel slits spaced at a distance d apart. The condition for maximum intensity is the interference in the interference pattern is going to be this. It's going to be the same condition as for a two-source pattern, but for the grating, the maxima are very sharp and narrow. So let's take a look and let's kind of see what's up with this. All right, so we've got a point source, we've got a straight edge, we've got what's being illuminated over here, and we have what is considered to be a geometric shadow. Geometric optics predict that this situation should produce a sharp boundary right here between illumination and solid shadow. In other words, if light behaved only as a point source, then what we should see geometrically is that the light comes in, gets stopped here, and then those particles would continue on here and strike this particular surface. That is not what we see. What we see here, again, is a little bit of illumination, as you can see here by this, this being sort of light and then eventually turning to dark. You can see here that this shadow does not have a sharp edge. So what's going on? Well, you can see here that we've got a razor blade that's halfway between a pinhole illuminated by monochromatic light and a photographic film. So you can see the photograph here of a razor blade, and you can see some sort of pinhole source, and that the fringe around the blade it's not completely dark. And here you can see an enlarged view of an area outside of the geometric shadow of the blade, just a blade's edge, where you can see this interference pattern, and you can see that it's gradual. It's gradual. It's not a complete light and dark situation. So we don't often observe diffraction patterns in everyday life because most ordinary light sources are neither monochromatic nor they're not point sources either. So if a frosted bulb were used instead of a point source, each wavelength of the light for every point of the bulb would form its own diffraction pattern. They would overlap, and to such an extent we wouldn't see an individual pattern. So this shows a diffraction pattern formed by a steel ball about 3 millimeters in diameter. And notice the rings, both inside and outside the geometric shadow, and the bright spot at the very center. The existence of the spot was predicted in 1818 on the basis of wave theory of light. A French mathematician, Poisson, during an extended debate in the French Academy of Sciences concerning the nature of light, Poisson himself was not a believer in the wave theory of light, and he published this apparently absurd prediction, hoping to deal a death blow to the wave theory. But the prize committee arranged for an experimental test, and soon the bright spot had actually been observed, and it had been seen, I guess, as early as 1723, but those experiments had gone unnoticed. So this is the Fresnel diffraction pattern formed by a steel ball 3 millimeters in diameter. So in figure 2615, which I guess is back here, both the point source and the screen are at finite distances from the object forming the diffraction pattern. This situation is described as near field diffraction or Fresnel diffraction. If the source, obstacle, and screen are far enough away that all lines from the source to the obstacle can be considered parallel, and all lines from the obstacle to a point in the pattern can, you are saying here that the screen is far enough away that all lines from the source to the obstacle can be considered parallel, and all lines from the obstacle to the point in the pattern can be considered parallel. The phenomenon is called far-field diffraction or Fraunhofer diffraction. Fraunhofer diffraction is usually simpler to analyze in detail than is Fresnel diffraction. So we're going to continue the discussion on that a little bit later. There is no fundamental distinction between interference and diffraction. In earlier sections, we've used the term interference for effects involving waves from small number of sources. Diffraction usually involves a continuous distribution of Huygens wavelets across the area of an aperture or a very large number of sources or apertures. The same principles are going to apply. So let's take a look at 26.5. So here we have a parallel ray monochromatic light coming in, striking a slit here, and then this is going to go through to a screen. Now, geometric optics predicts that the setup will produce a single bright band the same size as the slit. Guess what you don't see happen? This. So we can't use geometric optics to predict what's going to happen. Doesn't work that way. We are going to assume that the slit width A is much greater than the wavelength of the light. In reality, what you see is a diffraction pattern. So you've got a slit width A, and you divide the slit into imaginary strips parallel parallel to the slit's long axis, and each strip is a source of Huygens wavelets. So if the screen is close, then the rays from the different strips to a point P are not considered to be parallel. If it is distant, then the rays to P are approximately parallel. A converging lens images a Fraunhofer pattern on a nearby screen. So for two strips shown here, and again, remember that the strips here are basically going to be taking this length right here and dividing these dividing this length into little cut pieces. These are the strips that it's referring to. So for say two strips that are shown here, the path length to P is going to be A divided by 2 times the sine of theta. When this is equal to 1/2, then the light cancels at P. This is true for the whole slit, so P represents a dark fringe. Theta in this case is usually very small, so we can use these kinds of approximations. Again, this is all about trying to make things as simple as possible. So in this particular case, in order to simplify the math, we're going to take the sine of theta is equal to theta, as well as the tangent of theta is equal to theta, because it makes things a little easier. So the condition for the dark band, if you remember back from the earlier section, we're going to relate that into distance r, the separation between the slit and the screen. So you can see here the single slit diffraction, a dark fringe is going to be related in this fashion. In the straight ahead direction, sine of theta is equal to 0 as a bright band, and in this case, the light from the entire slit arrives at P in phase. So you got a few problems there that you can work on. So now let's go to 26.6. Okay, so in this particular case, we've got several different slits going on over here with rays that are coming through. The maxima is going to occur when the path lengths or the path difference for the adjacent slits is going to be a whole number. So these differences in the path lengths here, you will see maxima occur here when this holds true. You will see minima when this occurs. So you've got two slits here producing one minimum between the adjacent maxima. 8 slits produce larger or narrower maxima in the same locations, separated by minima that you have going on here. So you got a maximum here, and then you got minimum going on here, and then you got another maximum, and then you'll have more minimum, so on and so forth. 16 slits, you're going to see a maximum here, here, and here with a whole bunch of minima in between. So an array of a large number of parallel slits, all with the same width A and the spaced equally distance, is going to be called a diffraction grating. That is referring to this. And so you can see this is what's being made here. You can see the angle here. All of these distances are D. And again, the D sine theta came through from the basically what we saw earlier in these section videos here regarding this is going to be the difference in the path lengths and whether or not it is related as a maxima or a minima depending on the values here of M.